So then proper definitions here. Diagram a bit blur. So this is in particle form, air particle. So you see compression here as a region of high pressure. That means you have a lot of air here. Then the low pressure area you have less particles. And how you get this region of high pressure and low pressure, right, is because the particles will, each of these particles will move left or right. So if you have a lot moving right side and then they all cluster here, that means it's high pressure. Okay.
Yeah.
So then you have your definition. Compression is a high pressure region area where air particles are pushed together. Rarefaction are low pressure regions, particles are pulled apart. This one, they may ask. Possible definitions. Possible definition question, so you need to know. Yeah, down here. So what happens is your longitudinal wave can be converted into something like that.
Displacement distance graph.
This is the pressure distance graph. There's a displacement graph also. The pressure distance graph is what happens is they measure the pressure of each region and then they plot. So the center of the compression is the area where it has the highest pressure. So that's why down here there's peak. Then the center of the rarefaction, right, has the lowest pressure. So it's like that here. So if you have this, you will see a wave that resembles the transverse wave. Then another way is back to this. Some books, right, some drawings, some graphs, they will tell you that they plot the movement of the air layers. They plot the movement of the air layers. Plotting the movement of the air layers, right, will give you the displacement distance bar. When you plot it, right, you will also get a sine wave like that if you plot the displacement of each air layer. So that's how you get the graph that they show you later. So back to this, there are two types of graph you get. Okay, that's how you get your transverse looking wave graph from the longitudinal wave. They either do a pressure distance graph for sound, or they plot the displacement of the particles in each air layer, and you will get a transverse looking graph too. Or you call it's actually a sine wave. Do you do AMF?
No.
No, okay. So it's a graph. That shape, right? This shape, right? Some teachers will say it's a sine graph because sine graphs look like that for AMF, but you don't. So I will call it the transverse wave looking thing or transverse looking graph, blah blah blah, whatever you call it. So the most important thing is you know what I'm saying. Okay, how is the sound wave generated from a source? One line answer. What do you think it is? Yeah. So vibrations takes place, then you create a sound from there. Then if they ask you explain how sound is being formed, right? How is or generated from a source, right? Then it is instead of giving 1 mark, they give you 4 or 5 marks. Then you have to describe this. Okay, next. So you have to give them the definition. If this is the official definition, then if it's in your book, if your teacher gives you this, then you can follow this. Okay?
Yeah.
So you take the official definition from your school text, school notes, or from the school teacher. I should have a definition
School
of
notes
this.
give this as the definition.
Then you just give this to them. Okay?
Yeah.
Yeah. Next one. Okay, rarefactions, wrong spelling. So you give them the official definition that your school teacher gives. Okay, 1C. Okay, write a proper answer. Exam standard. Explain why astronauts cannot hear the explosion from a nearby planet in the space. This is the same question I gave just now about a supernova. Sound requires a medium to travel. Sound requires a medium to travel. And since space is
SOUND.
yes.
SOUN.
Yes, I
I
realize.
put SOUN.
Travel also wrong spelling. Requires a medium to travel or transmit.
ERAVEL.
Yes. So then since space is a vacuum, the astronauts will not be able to hear the explosion in space. Yeah, okay, makes sense. So this is a like a 1 mark question most of the time. So we have 3 equally spaced rows of lines in diagram 1. So it represents the air molecules before the sound wave passing through them. So 1, 2, 3, I think. Three equally spaced rows of line. Then they say the lines in diagram B represents the position of the same rows when a sound wave passes through it at a particular time. 4, 5, 6, compression 4, 5, 6, and then maybe 16, 17, 18. This is correct. You only need to state 3. Next one, state 3 consecutive numbers in diagram which represent a rarefaction. 10, 11, okay. This one. This one, you need to measure. You tell me where you measure, then after that, then we will calculate together because this answer depends on how big your screen is. You have to tell me where you measure, from where to where. Tell me which, the one wavelength, right, is between which number and which number on diagram B.
5 to 17.
Okay, so 5 to 17, so this is one wavelength. Then tell me how much, what is the length of the wavelength from 5 to 17 you measure with your ruler? 13?
Yeah.
13 centimeter. Okay, so then they say if the diagram is drawn in a scale of 1 to 5, that means 1 centimeter on the diagram B, right, represents 5 centimeters.
5 cm.
So it's 5 times 13.
Times 30.
Yeah. So that it will be your wavelength.
65.
Yes. So your wavelength will be 65. Okay. So the answer will change if you use a different computer, unless you get the piece of paper you print out. Even print out also it will look different because of the resin, the size of the paper and all that, or you print how many pages on one page. Yeah.